Hi everyone, welcome to our physics class. In the previous class, we have studied about properties of magnetic field lines, derivation of expression for magnetic field at a point and axis of a current carrying solenoid. Show that current carrying solenoid as a bar magnet, and derivation of expression for torque acting on for magnet that is placed in the presence of uniform magnetic field. So this is magnetism and matter part 4. So in this class we are going to discuss about a very simple derivation, that is expression for potential energy of a magnetic dipole is placed in the presence of uniform magnetic field. Okay, well, let's start today's class. So this is derivation of an expression for potential energy of a magnetic dipole placed in a uniform magnetic field. Okay, first here, let us consider a bar magnet. What is the meaning of bar magnet? Bar magnet, any rectangular or cylindrical object that has a magnetic field. Any rectangular or cylindrical object that has a magnetic field is called a bar magnet. So each and every magnet has two poles, south pole and north pole. So what is the magnetic strength of south pole? Magnetic strength of south pole is minus Qm, and magnetic pole strength of north pole is plus Qm. So the pole strength of south pole is minus Qm. Pole strength of north pole is plus Qm. Okay. So when magnetic charge that is there in the presence of magnetic field. Actually, here bar magnet is placed in the presence of uniform magnetic field. When a magnetic field in a region is said to be uniform, if it has the same magnitude and same direction at all points of that region, it is uniform magnetic field. So here the magnetic field lines is straight, parallel, and equidistant. That means here the uniform magnetic field acting in the plane of the diagram. Okay, so if a magnetic charge is placed in the presence of magnetic field, it will experiences force. Okay, so the force acting on plus Qm, that is Fn vector, that is equal to Qmb vector, and the force acting on the south pole is Fs vector, that is equal to minus Qmb vector. Okay, here negative sign indicates the direction of force acting on the south pole of bar magnet is opposite to the direction of the magnetic field. Okay, the force acting on north pole of bar magnet, that is along the direction of magnetic field, but the force acting on south pole of bar magnet, that is opposite to the direction of magnetic field. So here negative sign indicates the force acting on south pole of bar magnet is opposite to the direction of magnetic field. That means when a bar magnet is placed in the presence of uniform magnetic field, so two equal and opposite forces acting on bar magnet. Actually, that is couple. Two equal, unlike parallel forces whose lines of action is different, that constitute a couple. Okay, what is the effect of couple on a body? So when couple acts on a body, what happens? The body will get rotated, right? So the rotational motion is the effect of couple. So the rotational ability of couple is called the moment of couple, that is torque. Okay, what amount of torque acting on a ball magnet if it is placed in the presence of uniform magnetic field? So when a ball magnet is placed in the presence of uniform magnetic field, what happens? Torque, torque acting, torque acting on ball magnet. So the torque acting on ball magnet, torque acting on ball magnet uh, in presence of uniform magnetic field is how much? That is tau is equal to magnitude of one of the force. Magnitude of one of the force is QMV, and the perpendicular distance between the two forces. So in the triangle, let us consider here this point as O. So in the triangle S and O, the triangle S N O. Actually, we want here the perpendicular distance. Sine theta is equal to perpendicular divided by hypotenuse. So Sn is actually distance from S to N, south pole to north pole, that is magnetic length. So that value is 2n. Sine theta is perpendicular divided by hypotenuse. Perpendicular, that is ON, hypotenuse is 2n. So perpendicular ON is 2l sine theta. The perpendicular distance between the two forces is 2l sine theta. So tau is equal to Qm into 2m. What is that? That is magnetic dipole moment. Magnetic dipole moment is the product of pole strength and the magnetic length. So tau is equal to mb. Tau is equal to mb sine theta. So call this as equation number 1. Okay, so this is the torque acting on a ball magnet if it is placed in the presence of uniform magnetic field. If the magnetic dipole ball magnet is rotated against the action of the torque. So this point is very, very important. When a ball magnet or magnetic dipole is rotated against the torque, against the action of torque, what happens? Work has to be done. Work has to be done. So actually, this work is stored as the potential energy. That is potential energy of the dipole. So the work done in rotating the dipole through a small angle d theta. Okay. Here, small amount of small amount of work done, small amount of work done in turning or rotating the dipole. Small amount of work done in rotating the dipole against torque. Against torque through a small angular displacement d theta is dw is equal to dw is equal to so tau into d theta. Is it not? So in case of linear motion, work done is force into linear displacement. So in case of angular motion, that means the rotational motion, work done is equal to torque into angular displacement. So here small amount of work done in rotating the magnetic dipole against torque through the small angular displacement d theta, that is tau into d theta. So dw is equal to, what is the value of tau? Tau is mb sine theta into d theta. dw is equal to mb sine theta. So therefore the total work done for the total work done in turning, total work done in turning or rotating the dipole from the initial angle theta 1 to theta 2 is. So what we have to do now? Just integrate the above equation on both sides. Integration of dw is equal to integration of mb sine theta into d theta. So the limits varies from theta 1 to theta 2. Okay, right? So integration of dw is w, right? That is equal to, so while integration, the constant terms that should be taken as outside. So here the magnetic dipole moment and magnetic field is constant. So mb is taken as outside. So mb integration of theta 1 to theta 2 sine theta into d theta. So w is equal to mb integration of sine theta. What is the value of integration of sine theta? It is minus cos theta. The limits varies from theta 1 to theta 2. So after that, the minus is taken as outside. The minus mb of cos theta. The limits varies from theta 1 to theta 2. So w is equal to minus mb. So first we have to apply the upper limit, that is cos theta 2 minus, and then apply the lower limit, cos theta 1. So actually this work done is stored as the potential energy. Okay, W is equal to minus mb cos theta 2 minus mb of cos theta 2 minus cos theta 1. So this work done, is stored as potential energy. Means W is equal to U. So U is equal to minus mb of cos theta 2 minus cos theta 1. So after that, here we have to take a natural choice. To take natural choice. So the natural choice is theta 1 is equal to 90 degree, and theta 2 is theta. Theta 2 is theta. So u is equal to minus mb of cos theta minus cos 90. Cos 90 is 0. So u is equal to minus mb cos theta. So in vector form, so this equation can also be written in the form of u is equal to minus m vector dot b vector, or in other words, u theta is equal to minus m vector dot b vector. So this is the expression for the potential energy. Expression for potential energy of a magnetic dipole or Bohr magnet. So after that, let us discuss about some very important special cases. So case 1. First case is if m vector is parallel to b vector, then what is the value of theta? Theta is m vector is parallel to b vector. What is the direction of m vector? Actually, here the line joining from south pole to north pole. What is this? This is the magnetic axis, magnetic dipole axis. What is the direction of magnetic dipole axis? That is always directed from south pole to north pole. Direction of magnetic dipole axis is from south pole to north pole. The direction of magnetic moment, is same as that of the direction of dipole axis. So theta is the angle made by magnetic direction of magnetic dipole moment and the direction of the magnetic field. So if m vector is parallel to b vector, then what is the value of theta? 0. Theta is equal to 0 degree. Okay. Then tau is equal to mb sine 0. Torque acting on the Bohr magnet is 0. But here we have to calculate the potential energy by using this mathematical expression. So u is equal to u 0 degree, that is equal to minus mb cos 0 is 1. So in this case, the potential energy of magnetic dipole is minimum. The potential energy of magnetic dipole is minimum, and actually this position is called position of stable equilibrium. So this is the position of the stable. So this position of Bohr magnet is called the position of stable equilibrium, and in this case the potential energy of the magnetic dipole is minimum and negative. Okay, then the next case, case B. If m vector is perpendicular to b vector, m vector is perpendicular to b vector, then what is the value of theta? theta is 90 degree. Okay, theta is equal to 90 degree. So the potential energy is minus mv cos 90. Cos 90 is 0. So this is the position of, this one is the position of zero energy. This is the position of zero, zero energy. In this case, the potential energy of magnetic dipole is zero. Okay. So, and the last case. So, if m vector is anti-parallel, anti-parallel to b vector, then what is the value of theta? Then the value of theta is 180 degree. So u 180 degree is minus mb cos 180. Cos 180 is minus 1. Minus into minus plus. In this case, the energy stored in Bohr magnet is plus mb. Okay. So this position of Bohr magnet is called the position of unstable. This is the position of unstable equilibrium, and in this case the potential energy of magnetic dipole is maximum. Okay, so this is very important for 3 mark. Okay, thank you.